Three-phase motor current calculation. Our goal in this lesson is to learn how to calculate the full load current of a three-phase motor. Then we will see which electrical components should be selected based on this current. This is a very important step in motor design and electrical panel selection. In sections 1 and 2, we introduced the main formula. The current is equal to the output power divided by the square root of 3, multiplied by the line voltage, multiplied by efficiency, and multiplied by the power factor. Key points. If the power is given in kilowatts, multiply it by 1000 to convert it to watts. The line voltage is usually 400 volts in European standards, and 480 or 208 volts in the United States. Efficiency is typically between 0.85 and 0.95, and the power factor is usually between 0.8 and 0.9. Always write efficiency and power factor in decimal form. For example, 90% means 0.9. Example 1, a 15 kilowatt motor, 400 volts, 90% efficiency, and a power factor of 0.85. Calculated current, 28.34 amperes. Now, what do we do with this value? Circuit breaker selection, MCB or MCCB. For a motor with 28.34 amperes, the breaker is typically selected at about 1.25 to 1.5 times the rated current. This gives a range of approximately 35 to 42 amperes. In most cases, a 40-amp breaker with a C or D tripping curve is selected. The D curve is more suitable for motors because they have high starting currents. Contactor selection. The rated current of the contactor should be at least equal to the motor's rated current. However, it is better to choose one size higher. For a 28-amp motor, a 32-amp or 40-amp contactor is suitable. Common brands include Siemens, Schneider Electric, ABB, LS, or Hyundai. Thermal overload relay, or bimetal. The overload relay should be set to the motor's rated current, which is 28.34 amperes. Select a range such as 25 to 35 amperes, and then set it to around 28 amperes. This device protects the motor against overload conditions. Cable selection based on NEC or IEC standards. For a 28-amp current, a 6 square mm copper cable is sufficient according to IEC standards. In the United States, a 10 AWG conductor is appropriate. If the distance is long, a larger cross-sectional area should be selected. This is the practical application of a simple number. Example 2, a 22 kilowatt motor, 415 volts, 92% efficiency, and a power factor of 0.88. Current, 34.86 amperes. Important note, as the voltage increases from 400 to 415 volts, the current decreases. This follows a general electrical principle: higher voltage results in lower current for the same power level. Horsepower to kilowatt conversion. A 25 horsepower motor is equal to 18.65 kilowatts. Its current is calculated as 35.23 amperes. Practical note: if only the horsepower value is written on the motor nameplate, you now know how to convert it into kilowatts and calculate the current. In the American market, motors are usually rated in horsepower, while in Europe they are mostly rated in kilowatts. Motor nameplate section. This is a real ABB motor nameplate. Rated power, 15 kilowatts. Rated voltage, 400 volts for delta connection, and 690 volts for star connection. Rated current, 28.5 amperes in delta, and 16.5 amperes in star. In 400 volt systems, this motor must be connected in delta. In 690 volt systems, it must be connected in star. The nameplate also shows an efficiency of 90%, a power factor of 0.85, insulation class F, and duty type S1, which means continuous operation. Now, take a look at the table. There are two current columns displayed side by side. The first column is based on an efficiency of 90% and a power factor of 0.85. The second column is based on an efficiency of 92% and a power factor of 0.88. Notice what happens. For a 15 kilowatt motor, the current drops from 28.34 amperes to 25.65 amperes. That means just a 2% increase in efficiency and a 0.03 improvement in power factor reduces the current by 2.7 amperes. Now look at a 30 kilowatt motor. The current decreases from 56.7 amperes to 51.3 amperes. That is a reduction of 5.4 amperes. So, what does this mean in practice? Smaller and less expensive cables. Smaller circuit breakers and contactors, with lower cost. Less heat generated inside the electrical panel. And lower electricity costs throughout the life of the motor. A motor with higher efficiency, such as an IE3 or IE4 motor, may have a higher initial purchase price. However, in many cases, the additional cost is recovered within a relatively short period of operation. That is why you should always pay close attention to the motor's energy efficiency rating. Before using the formula, remember these important points. First, always use the motor output power, not the input power. Second, use the line voltage, not the phase voltage. Third, an efficiency of 90% must be entered into the formula as 0.9. Fourth, a power factor of 0.85 is used as 0.85 in the calculation. And finally, this formula is valid only for a balanced three-phase system.